Welcome to Electron Line, and now in this case we're going to put a charge inside our spherical conductor that has a cavity. So here's our spherical conductor. There's the cavity inside the conductor, and inside the cavity we place a small charge, a -5 microcoulomb charge, while at the same time we place a positive 8 microcoulomb charge on the spherical conductor that has that cavity. What will happen is, of the 8 microcoulombs of charge, 5 microcoulombs will reside on the inner surface of this conductor because there's this -5 microcoulomb charge on the inside the cavity. So that will draw some of the positive charge equal in amount to the surface on the inside of the cavity here, or on the inside of the conductor right near the cavity, to compensate for the -5 microcoulomb of charge. So you have an electric field that will be directed from the positive to the negative like this. So there will be an electric field in this direction inside the cavity, like so. And of course, then the best way to draw this here is that the electric field inside the cavity will of course be directed inward like that. Okay, now what will be the electric field inside the conductor, between the inside and the outside surface? Well, we'll find it out in just a moment. And then also, what will be the electric field outside the conductor, like let's say a distance r3 away from the center of the conductor here. All right, let's use the equation, or Gauss's law, to find all 3 electric fields. So first we're going to find the electric field inside the cavity around the -5 microcoulomb charge. So we can say that E dot dA, so E times the area of that sphere. Remember that the electric field will be directed in the same direction, parallel to the normal of the surface. So we have a Gaussian surface right here, so the normal of the Gaussian surface will stick straight out, and the electric field either will be inward or outward at that point, so they'll be parallel. So we've taken the cosine of 0 degrees or the cosine of 180 degrees. Of course, the cosine of 180 degrees is negative, which would indicate the electric field is pointing inward, which already we understand because the electric field will go from positive charge to negative charge, so the electric field inside this cavity will have to be directed inward towards a negative charge. So E times the area, which will be 4 pi times r1 squared, r1 being the radius of the inside Gaussian surface right here. So r1 right here is this distance right here, and so that will equal the Q inside, which is a -5 microcoulombs divided by epsilon sub naught, epsilon sub naught being the permittivity of free space. So, well, let me just put the Q inside here. I'll just do it in a general sense first, then we'll put numbers in later. So Q inside, that's better. And so that means that the strength of the electric field will be equal to Q inside divided by 4 pi epsilon sub naught times r1 squared. And so if we then say 1 over 4 pi epsilon sub naught is K, I should say, that means E1, let's call that E1 there, that would be the electric field inside the cavity right there, that would be E1. E1 is equal to K times Q inside divided by R1 squared. So depending upon the size of R1, we can see that the strength of the electric field will diminish as we go further and further away from the inside charge, but that in general, the electric field strength will be K, which is 1 over 4 pi epsilon sub naught, times the Q inside, which will be the -5 microcoulombs, divided by R1 squared, and R1 simply be the distance from the center to wherever we want to place the Gaussian surface, wherever we want to find out what the strength of that field is. I didn't put any numbers in, but let's say that the inside radius, let's say that this radius right here, let's call this 20 centimeters, and let's call this one here 40 centimeters. So that means that inside the cavity, it's anywhere from 0 to 20 centimeters, which would be the R1 in here. K is 9 times 10 to the 9, and Q inside will be the -5 microcoulombs. Okay, what would be the electric field strength inside a conductor? Well, we do the same thing. So here we have E2, which is equal to, let me write, E2 times A is equal to Q inside divided by epsilon sub naught. And of course, what would be the area of the Gaussian surface? That would be between this inside surface of the conductor and the outside surface of the conductor. So the Gaussian surface here would be R, the radius to that would be R2. I have it drawn right here. So it would be E2 times 4 pi r2 equals Q inside. Now the interesting thing about the Q inside the Gaussian surface, it'll be the minus 5 microcoulombs here plus the positive 5 microcoulombs there. Let me put the cap down here, so it'd be minus 5 microcoulombs added to the plus 5 microcoulombs divided by epsilon sub naught. Now notice that these two will cancel each other out. That means there's zero net charge inside. So we have E2 times 4 pi R2 equals 0 divided by epsilon sub naught. So E2 equals 0. There is no electric field inside the conductor between the inside surface and the outside surface of the conductor. Wow. That's interesting, but that's what Gauss's law tells us. And then for the third region, that would be outside the outside portion of the conductor. So now we can say that E3 is equal to, or let me not jump ahead of myself, it'll be E3 times the area of the Gaussian surface that's now out to here. So it would be determined by this Gaussian surface is equal to the Q inside divided by epsilon sub naught. So here that becomes E3 times 4 pi R3 squared. Ooh, do I have this correct here? I want to square it, I just noticed I made a mistake there. The area is 4 pi r squared, not just 4 pi r, that would make sense. So 4 pi r cubed, or sub 3 squared, all right? And that equals the Q inside. Now what is the Q inside this big sphere right here, this big Gaussian surface? Well, we have the minus 5 microcoulombs on the object inside, plus the plus 5 microcoulombs on the inside surface of the conductor. And then we have an additional plus 3 microcoulombs of charge on the outside of the conductor. Notice that these two cancel each other out, but we still have a net charge of 3 microcoulombs engulfed in the outside Gaussian surface divided by epsilon sub naught. So finally, when we solve that then, we can then conclude that the electric field outside the conductor, E3, is equal to the net charge, 3 microcoulombs, divided by 4 pi epsilon sub naught times the radius r3 squared. And of course, 1 over 4 pi epsilon sub naught is simply the k. And so we can write this as k times q net divided by the radius out there squared, which again is the equation for the electric field outside a point charge. And if you're far enough away from the outside of the conductor, from the outside conductor there, right here, we can say that that will be the electric field. Q net is simply the total charge on all the objects inside the surface, which means the minus 5 microcoulombs and the 8 microcoulombs that was added. Net charge of 3 microcoulombs. And that's how we do that for the 3 regions of a spherical conductor with a charge inside the cavity.